Hi, this is Moser with a quick tutorial on getting to the quantum atom. After watching this video, you should be able to describe the quantum model of the atom, as well as trace and explain the observations that led to the development of the quantum model. You should already know what an electron is, and that electrons exist outside the nucleus. Ah, yes, the electron, small, negatively charged, zipping all over the place. There's just one problem. If opposite charges attract, well, yeah, this was a problem for particle physicists. The Rutherford model of the atom had those beautiful little electrons zipping all around the positive dense nucleus. But what particle physicists couldn't figure out is why the electron didn't just get sucked right into the nucleus. In order to solve this problem, they had to look at some other observations about light and energy, and this led them to a deeper understanding of the electron. It'll seem like we're taking a left turn off the road, but I promise you we'll get back to the electron. Just hold tight and follow along. So, light, visible light, you've seen it, you're seeing it right now. It's actually a form of electromagnetic radiation, and the electromagnetic spectrum includes everything from gamma rays and microwaves to radio waves, X-rays, and the visible light that you and I use to see. So, as early as the early 20th century, it was known that light behaved as a wave. Yeah, these are light waves. And like any other kind of wave, there are things about waves that we can measure. So the things that we can measure in a light wave are the same as we can measure in any wave: wavelength, frequency, and wave speed. Note that this is C. I feel like I've seen that somewhere before. So wavelength, if you've forgotten, is the distance from a point on a wave to the next example of that same type of point. So from crest to crest, or from trough to trough, or what the heck, from the middle of one sliding part to another. It's just the point where you've gone through an entire cycle of wave motion. That's a wavelength. Frequency, if you imagine this as an ocean wave and you imagine a pier out in the water, is the number of times that a given point, like a crest or a trough, would hit that pier per second. Speed, well, that's easy to understand. Speed is how fast something moves. The convenient thing for us is that all forms of electromagnetic radiation move with the same speed. That's 3 times 10 to the 8th meters per second. And the relationship between these three things is summed up in this handy little 3-part equation. C equals lambda v, or wave speed equals wavelength times frequency. What this allows us to do for any form of electromagnetic radiation, because we know C, if we know the wavelength, we can compute the frequency. If we know the frequency, we can compute the wavelength. Pretty cool. Now, we had known all these things about waves and about light waves, but there was this weird observation. So, in 1887, it had been observed that when you took a piece of metal which was conducting electricity, and everyone knew by then that you could conduct electricity through a metal, add electricity to this side, electricity will flow off this side. Super cool. Well, if you shone a light on it, specifically an ultraviolet light. Boop, 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 boop. Beams of light coming down on it, little waves. There, I changed them, little waves. Well, what was known was that when you did this, the rate of electrical conduction would speed up. It would actually conduct more electricity per unit time. What was even stranger? The light had to be at a minimum frequency or there was no effect whatsoever. This was called the photoelectric effect, photo meaning light. Based on these observations, Max Planck, that's this guy right here, suggested that materials, such as those metal electrons, could only gain and lose energy in finite discrete packets. He called them quanta. And he said that 1 quantum was the minimum amount of energy that could be gained or lost. He came up with this simple little equation, E equals hv, where E is the energy that the material is gaining or losing, H is a constant, 6.6 626 times 10 to the negative 23rd joules per second, and V is the frequency of the radiation that's being emitted. H came to be known as Planck's constant. So what's he saying? Well, he's saying that energy occurs in chunks, in pieces. Okay. Now, this guy, and that there is a very young Albert Einstein, takes Planck's idea that energy occurs in these discrete packets, and he takes it a little further. Based on the idea of the photoelectric effect, that there are actually chunks of energy being given off, Einstein suggests that perhaps the light that's hitting the metal is also behaving as a particle. So in 1905, Einstein proposes the dual wave-particle nature of light and says that while light does behave like a wave, it can also behave like a particle. He calls the light particles photons. I know, this seems so unrelated. I promise you it's not. Though we are going to take what will seem for a moment like one more turn off the road. I promise you we'll be back on the main route very shortly. It had also been known for a very long time that when you sealed a gas in a tube under low pressure and ran current through it, it glowed. Well, this is kind of like the cathode ray tube. What was really interesting was that you could do it with other gases at low pressure. For instance, hydrogen. Oh, what a pretty pink glow. It had been proposed that the ground state of hydrogen was the lowest energy state possible, and that somehow when you ran current through it, you excited the gas. You raised it up to a higher energy level. Now, that's great, but we didn't really know exactly what that meant in terms of, where are we going with this? Electrons. It had been proposed, however, that the difference between ground state and excited state occurred in specific increments. Oh, what would that be? That would be quanta. Yeah, quanta. Those discrete packets of energy. Now, what was even more interesting was that when you took our glowing hydrogen and you took that pink glow and you ran it through a prism and it broke the light up. It broke the light up into 4 distinct bands. In other words, this wasn't just light in one part of the spectrum. This was 4 distinct bands with distinct frequencies. Wait a second. So those frequencies weren't continuous. They were out at these sort of intervals. If the difference between the excited and ground states represented a quanta of energy, the specific locations of these emission lines suggested that electrons existed in very specific energy states. This led to a brand new idea. Enter Niels Bohr, the Dane. And in 1913, Bohr proposed that electron orbits had varying energy levels, and this explained the emission spectra of hydrogen. He suggested that each electron in an atom was locked into a pathway or an energy level, and that they could move up if energy was added to the atom, but when they fell back to their original level, they would give off energy in the form of light. Hence, the glowing tube of hydrogen. This worked beautifully for hydrogen. However, when they started looking at larger atoms and larger elements, the theory fell apart a little bit. It's really just an improvement to the Rutherford planetary model, so this is often called the Rutherford-Bohr planetary model, or now it gets called the quantum planetary model sometimes. What's interesting is this is still the basic model that's used to teach electron configuration in introductory courses such as physical science. So you've seen the Bohr atom. You may have learned, if you remember or not, that certain numbers of electrons can exist at each energy level, and that those electrons determine the characteristics of the material. That's all good stuff. Now, we continue to discover things about the atom. And in 1927, Louis de Broglie, minor French nobility, imagines that based on the quanta of energy and the photons of light, perhaps, if light can behave as a wave and a particle, electrons, which we know are a particle, can also behave as a wave. This starts to explain why perhaps those electrons trapped in their energy levels don't crash into the nucleus. Now, two things happen simultaneously. What's really funny is that Erwin Schrödinger and Werner Heisenberg thought that they were in disagreement. So you have, by this point in your academic career, done equations for lines. And you know that for any line, you can find an equation that will describe where that thing is at some point in time. Great. Well, did you know you could do that in a three-dimensional space? Ooh, yikes. Well, Erwin Schrödinger developed a series of equations that treated electrons as waves. Oh, based on the work of de Broglie. The weird thing was that only certain frequencies would satisfy the equation. Now, at the same time, Werner Heisenberg was working with highly energetic particles and proposed what came to be known as the uncertainty principle, that it is not possible to know both the position and velocity of an electron, or any other particle for that matter, but that there was some defined uncertainty in attempting to measure their location. What do we get when we put all of that together? Well, that atoms have a dense central nucleus made up of protons and neutrons. That hasn't changed since it was proposed by Rutherford. That electrons are in specific areas outside the nucleus and moving constantly. Those rings or tracks of Bohrs have become fuzzy cloud-like areas based on Schrödinger's equations, and the exact location of the electrons is unknown. But we know that they're outside the nucleus, and we know that they're moving. The one holdover from the planetary model is the idea that there are main energy levels. Within that big, giant, fuzzy, cotton candy cloud, we can't know the exact position of an electron at any one point. That's courtesy of Werner Heisenberg. But when you solve for Schrödinger's wave equations, those wave equations give us three-dimensional areas where there is a very high probability of finding an electron. Those areas of high probability are called orbitals, and they have some pretty funky shapes, let me tell you. We'll look at those a little later. But when we put them all together, they just look like a huge fuzzy cloud. Imagine a bunch of mosquitoes swarming around your head. That's probably a pretty good graphic. So now, what do we know? Well, there's more than one model of the atom. Which one's right? It doesn't work that way. The planetary, the Rutherford Bohr planetary, and the modern quantum model both allow us to understand different things about the atom. So, each is correct. The quantum model gives us a more nuanced and detailed understanding of the electrons in the atom. But the Bohr model is a useful tool for talking about atoms, especially at an introductory level. So we tend to use both models to talk and think about atoms. That's it. That's how we got to the planetary model of the atom.